When we talk about heat in science, we're actually talking about thermal energy. Imagine all the tiny particles in a substance. They are constantly jiggling and moving. The faster those particles move, the hotter the object feels, and the more thermal energy it has. When you place a pot of water on a stove, you're transferring energy to the water molecules, making them move faster and raising the water's thermal energy. The term heat is just what we use for that energy transfer itself. It's easy to confuse temperature and thermal energy, but there's a key difference. Think of it like this. Temperature is the average speed of the particles, but thermal energy is the total energy of all the particles combined. A tiny spark from a match is incredibly hot, a very high temperature. But a swimming pool of lukewarm water has far more total thermal energy because it has trillions of times more particles, even though the average particle speed is lower. It's the difference between speed and quantity. So if thermal energy is the ability to cause change, how does it move? Heat transfer is the natural process where thermal energy flows from a hot region to a cold region. It's like gravity for temperature. Energy always wants to move down the thermal hill. This flow will continue until everything is the same temperature. That's why an ice cube melts in your hand. Your warm hand transfers heat to the cold ice cube until they reach a thermal balance. Thermal energy can be sneaky and moves in three distinct ways. The first is conduction, which happens through direct touching. Think of a metal spoon heating up in soup. The second is convection, which involves the movement of fluids, like boiling water or circulating air. And the third is radiation, which is the silent, wave-like transfer that doesn't need any matter at all, like the heat you feel from the sun. We'll look at each one closely. Let's start with conduction. This is heat transfer through physical contact. Picture a line of people passing a basketball down the line without anyone moving their feet. The energy is transferred through collisions. In solids, the tightly packed atoms bump into their neighbors, transferring their kinetic energy down the line. That's why if you hold one end of a metal rod and put the other end in a flame, the heat will travel right to your hand. Materials behave very differently when it comes to conduction. Conductors, like most metals, are great at allowing heat to pass through quickly. This is why cooking pans are made of metal. On the flip side are insulators, like wood, styrofoam, or air, which resist heat transfer. The handle of that same cooking pan is often made of an insulator like plastic to prevent the heat from burning your hand. Insulators are essential for keeping houses warm and drinks cold. The second method is convection, and it only happens in fluids, liquids, and gases. It's all about movement, driven by density. When a fluid is heated, its particles speed up and spread out, making it less dense. Because the hot fluid is lighter, it rises. As it rises, it cools, becomes denser, and sinks back down. This continuous rising and sinking creates a convection current, effectively carrying the thermal energy throughout the fluid. Convection currents aren't just limited to a pot on the stove. They drive massive natural processes. Think about the weather. Warm air near the equator rises, travels toward the poles, cools, and sinks, creating global wind patterns. Even deep inside the Earth, the mantle experiences massive convection currents that slowly move the continents. Convection is literally the engine for much of the motion we see on our planet. Finally, we have radiation. This is the transfer of thermal energy via electromagnetic waves, mainly infrared waves. The amazing thing about radiation is that it doesn't require any matter to travel. It can go through empty space. The best example is the sun. Its heat travels millions of miles through the vacuum of space to warm the Earth. If it weren't for radiation, we would be a frozen rock. Radiation interacts with surfaces in different ways. If a surface is dark and dull, it's a good absorber of radiation. This is why wearing a black shirt on a sunny day makes you feel hotter. Conversely, surfaces that are light and shiny are good reflectors. They bounce the radiation away, which is why emergency blankets are often silver and shiny. They reflect your body heat back to keep you warm. To solidify the concept of conduction, imagine putting ice in a warm glass of water. The fast-moving particles in the glass and the water are constantly colliding with the slow-moving particles of the ice. Through those direct molecular collisions, the kinetic energy is transferred, causing the ice particles to move faster and eventually turn into liquid water. It's a microscopic game of energetic tag. You experience convection every time you boil water for pasta. As the bottom layer of water is heated by conduction from the pot, it rises to the surface. The cooler, denser water at the top then sinks to take its place near the heat source. This circular motion ensures that all the water eventually gets heated evenly. That's why, even without stirring, the whole pot gets hot. Radiation is easy to spot. Just stand next to a roaring fireplace. You feel the heat on your face instantly, even though the air between you and the fire hasn't had time to heat up completely via convection. The electromagnetic waves are traveling from the fire straight to you. This is also how a toaster works. The glowing wires radiate heat to toast your bread without physically touching it. Let's bring back the big idea, the law of conservation of energy. This law applies to thermal energy too. It means that when heat moves, the energy doesn't disappear. It simply changes location or form. Think of it as an energy budget. If one object loses 100 units of thermal energy, another object or the surrounding environment must gain that exact 100 units. The total energy stays constant. In a transfer scenario, the conservation law is very specific. Heat lost equals heat gained. Imagine a hot metal coin dropped into a beaker of cold water. The coin will rapidly lose thermal energy, and the water will gain that exact amount of thermal energy. The overall thermal energy of the coin-water system hasn't changed. It's just been redistributed until they reach a balance. This redistribution leads to thermal equilibrium. Equilibrium means balance or equality. When two objects in contact reach thermal equilibrium, it means they have achieved the same temperature, and the net flow of heat between them stops. If you leave a hot cup of tea sitting out, it will eventually cool down until it's the same temperature as the room. At that point, it's at equilibrium with its surroundings. Not all substances heat up or cool down at the same rate. This is due to a property called specific heat capacity. It's basically a substance's thermal inertia, how much energy it can absorb before its temperature changes. Imagine a metal spoon and a wooden spoon both in the sun. The metal spoon, with its low specific heat, will get hot much faster than the wooden spoon, which has a higher specific heat. Water is a fascinating example because it has a remarkably high specific heat. It takes a massive amount of energy to change the temperature of water. This is why coastal areas have milder climates than inland areas. The ocean, which is mostly water, acts like a giant temperature regulator, absorbing huge amounts of heat in the summer and slowly releasing it in the winter, keeping the air temperature stable. Engineers and scientists need to be able to calculate exactly how much heat is transferred. That's where the heat equation comes in. Q equals m times c times delta T. Q is the heat transferred, m is the mass of the object, c is its specific heat, and delta T is the change in temperature. If you know how heavy something is and what it's made of, you can predict exactly how much energy you need to heat it up. Understanding conduction, convection, and radiation is crucial for engineering efficiency. For example, why do refrigerators work? They use insulators on the walls to minimize heat transfer via conduction and convection from the outside. Why do computers have fans? The fans create convection currents to move the heat away from the hot processor, which is using a metal heatsink for conduction. Every heating, cooling, or insulation system is a real-world application of these three heat transfer methods.